So basically what this says is compose the exponential function with the logarithmic function and you get the identity. Another identity that we'll be using today, the second one is this one, exponential function, let's say to the 3 plus 5. That's the same as exponential function cubed times e to the exponential function to the 5th. So on the right-hand side, this is the formula is multiplicative, but on the left-hand side, the formula is additive. Again, separable differential equation is you have some expression of x, some expression of y, and then you can separate them. So for example, see, this is an expression of x. There's y is not involved in this part of this formula, and then we have times, and there's some expression of y. X is not involved in this formula. So this equation is separable because we can separate the x's and y's and consider them together as a product of two expressions. One is negative 2x times y. Okay, it's a separable equation. So how do we solve separable equation? Very simple. Let's write this equation in this convenient way. So we'll say that derivative of this function y with respect to x. Sometimes they use t as the independent variable, and sometimes x, all the same. So I'm going to just rewrite this differential equation in this way. Y prime is the same as dy over dx. Or when the function is a function of t, then we'll say dy over dt. The same thing. And then the right-hand side, this is the product of those two separable factors. One is the factor of x, negative 2x. See, times, not addition. This is times, and then the other function of y. So times y. Okay, and then let's do the same method, so to say, that we did for substitution. So let's multiply and think of this that way because this is really a symbol. But we can think as a multiplying through formally by this factor dx. So on the left-hand side, I get dy equals negative 2x times y. If we don't remember, we can say, okay, so this is going to be equal y to the negative 2, and I'm going to add 1 plus 1 divided by this exponent, so divided by negative 1. And that's going to be equal, what's antiderivative function x squared by 2. X squared by 2 and some constant c I add. So this is the same as, this is y to the negative 1, y to the negative 1 divided by negative 1. And that's equal to x squared. Let me just say this is 2c divided by 2. The same thing. I just want to see the common denominator. So I'm going to have x squared plus 2c divided by 2. Okay, so now this is what? This is y to the negative 1. This is the same as 1 over y. And there's a negative, so I have negative 1 over y. And that's equal to x squared plus 2c divided by 2. Okay, so maybe I can multiply both sides by negative 1. So I'm going to get 1 over y. That's equal to negative x squared, negative 2c. And then divided by 2. Okay, and you know solution is y. I want to get y by itself. So if I do the reciprocal on the right-hand side, I get this is the same as 2 divided by negative x squared minus 2c or plus 2c. Really, I can say plus any number a because it doesn't really matter. It's just negative 2c. I can say plus any number a where, and then I can say where a is any constant. The constant function 0 is also a solution to this differential equation. But now, no matter what the constant a you take, there's no way you can generate this solution just by manipulating this constant a. So in this example, my solution set consists of this formula, and I have to separate one, and I have to say, okay, those are all solutions to this differential equation. First of all, they are given by those formulas where a is any constant, as well as this constant function 0 is also a solution of this differential equation, but it's not involved, so to say, in this family, because there's no way you can generate this function 0 by just using different a's. Okay, so that's all solutions to this differential equation. So what we did was we multiplied both sides of this by dx. That will give me dy equals this dx. Okay, and now what I want to do is I don't want to see the y squared. So I'm going to divide both sides of this equation by y squared. That will give me this equals that. When I integrate, I get one solution, or really many solutions, but given by this formula, as well as the extra obvious solution, because obviously 0 is the solution of that. You can say this is the same as 1 over x times y. So you can separate the x's and y's. So we can write this equation again, dy over dx equals 1 over x times y. So I'm going to multiply both sides of this equation by dx. So I'm going to get that dy is equal to 1 over x times y dx. And now what I want to divide both sides of this equation by, I want to divide this by y. So I get dy over y equals 1 over x dx. Okay. Okay, so integrate left-hand side, integrate the right-hand side. This respect to this respect to y, I get ln of absolute value of y equals ln of absolute value of x plus some constant c, and the same trick, apply the exponential function. I get e to the this expression, I get absolute value of that equals e to the this expression absolute value of c times, well, e to the c. But then I can replace this by any constant a. So, and then when I skip the absolute values, I get that y is equal to essentially some new constant c times x. Those are all the solutions, very simple. So for example, take this is my x-axis, and this is my y-axis, and take the solution that corresponds to c equals 1. Then we have the solution y equals x. Very simple function. Y equals x is a solution to this differential equation. Take this function c equals 2. Then I have this function y equals 2x. Very simple function. This function looks like this, and this is another solution to this differential equation. Take this function c equals 3. I'll take the last one, okay, but you see all the solutions now. Then I have the solution y equals 3x. So y equals 3x, that's the function. Okay, take a negative number and you have all the solutions. Looks like this. Those are all the solutions. And let's say that the equation says, the differential equation was this, and let's say the equation says find the function y such that y of maybe 1 is equal to 2. Okay, so add 1 is equal to 2, so what's going to be the constant c? The constant c is going to be 2. So the function y of x equals 2x is a solution of this differential equation as well as satisfies this condition, because c y of 1 is going to be 2 times 1, but 2 times 1 is 2. Okay. So that's an example, and that's what we mean by initial value problem. Initial value problem consists of a differential equation like this one and one condition. For example, y, the function at 1 is supposed to be equal a given value. So if you want another condition, I can give you the function at 1 is equal to, let's say, 7, for example. Well, what's the corresponding solution? Y of x equals 7x. See, every solution of this differential equation has to be of this form c times x, and the only point is to find the appropriate constant c. So obviously in this example, that would be 7. So this is this is the direction field of this equation that we have just solved. So this is the function y equals x. This is one solution. This is the function y equals negative x. This is another solution. This is the function y equals 2x. Okay, and so on and so forth. Have to say now in general how to sketch a direction field. I think we mentioned this example. What time is it? Okay, so what we mentioned this example last time. So take, for example, c equals 1 and consider the right-hand side of this equation, t plus y equals c equals 1. So y is going to be equal 1 minus t. If we take t to be 0, then this one. Okay, so the function, the Isaac line will look like this. This is the line. This is the line. This is the line y equals t or 1 minus t. Okay, but then if you take any point on this line, the slope is going to be 1. The slope is going to be 1, and this is a slope 1. 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 Slope 1, slope 1, slope 1, and so on and so forth. Do the same for c equals, for example, -1 or c equals 0, and so on and so forth. That will give you how to sketch the direction field.